37.2 and 37.3 go over how neurons work and membrane potential, action potentials. There's a video in Mastering Biology that you should watch, which is titled How Neurons Work. I'll try to upload a link to it, but please make sure that you watch it before proceeding into 37.2 and 37.3. Nerve and neuron impulses have to do with a form of electricity. And the way that neurons work is first by having a membrane potential. And there needs to be a difference in the electrical charge across a cell membrane in order for that signal to be sent. A difference in charge is also known as voltage, and being shown in the picture shows a technique in how that membrane potential is measured using a voltage recorder, in showing that there's a difference in the charge inside that neuron versus the outside when that neuron is placed in a type of solution. Looking at the membrane of a neuron, there are several proteins which are responsible for maintaining a negative potential, membrane potential inside the neuron. So looking at the diagram, you can see that there are several potassium channels. This is an ion channel that allows the potassium ion to move with the concentration gradient. So within the cell, typically there's a high potassium concentration. Outside the cell, there's a pretty low potassium concentration. So the potassium is able to flow from the inside to the outside thanks to the many different potassium ion channels, and it goes with the concentration gradient. Now, there's not as many sodium channels in the membrane, and outside the cell, there's a high sodium concentration. Inside the cell is a low sodium concentration. So it's a lot more difficult for that sodium to come into the cell to balance out that concentration of sodium, but it is able to move with the concentration gradient. It's just at a slower rate for the sodium to come inside. Now, if we just had those ion channels working, over time, there would be equal charges on the inside and the outside of the cell, which isn't good for voltage, isn't good for there being a charge difference. So the way that the negative membrane potential is maintained is by and thanks to the sodium-potassium pump. The sodium-potassium pump is in purple on the left, and it's another type of membrane protein that it actually works against the concentration gradient. So again, typically outside that cell, there's a lot more sodium. Inside the cell, there's a lot more potassium. So the sodium-potassium pump, and I think it's going to get more into this in section 3 in terms of the detail, but for right now, know that the sodium-potassium pump goes against the concentration gradient. To give you quick numbers, there are for every 3 sodium that are pumped out where there's already lots of sodium, there's 2 potassium ions brought in where there's already a lot of potassium. Now, the reason that this is important, we're not getting into, this is pretty much the whole slide for section 2 that you're going to be held responsible for. You're not going to have to know the equilibrium potential formulas, the Nernst equation, any of that. You need to know like the types of ions. You need to know what those channels are doing, what the sodium-potassium pump is. and to give you a quick answer without getting into too much detail, anytime there's net movement across that membrane, it's going to generate potential, electrical potential or voltage. So just the movement across in that imbalance of charge is going to allow for that charge difference, which ultimately causes the impulse to be sent in the neuron. I do need to add, because I don't think I said, when I say going with the concentration gradient, that always means from a high to a low concentration of something. If I say go against the concentration gradient, it would be just the opposite. Please make sure that you understand that.